Okay, today is very exciting. We're going to talk about uniform continuity. And uniform continuity is very intimately tied together with the Cauchy sequences that we saw in the last unit. So to begin with, to make an overall announcement here that uniform continuity, I'm going to be writing this down a lot. So when I write uniform continuity, I may often use the abbreviation UC for uniform continuity. So UC does not refer to unit circle like it did in trig class. It refers to uniform continuity. Okay, to begin the discussion, recall that the definition of continuity was given at a point initially. Our very initial definition was how to say or how to represent that a function was continuous at a point C. So, given a function f going from some domain D to the real numbers, for f to be continuous on all of the domain D, we required the following. We required that for all C in the domain and for all epsilon greater than 0, there was a delta greater than 0, such that if, let's see, we'd need x to be in the domain, of course, and we would need our distance from C to be less than delta, and together these would have implied that the distance of f of x from f of C would be able to be made less than epsilon. Right, so for things that got really close to C, we could see that their functional values must have gotten very close to f of C. Now, note very well here that the choice of the delta, we had to choose a delta in these arguments, and when we put our g-cap on and chose our delta, it depended on possibly the point in the domain, the C, or the point where we were working in the domain, and also it depended, of course, on how big the epsilon window was around the f of C. So it depended on these two things, possibly. Right? Maybe it didn't matter, but at least, at the very least, maybe we had to worry about them. Okay? We always had to worry about epsilon, but sometimes the point didn't really affect it, as we'll see when we look at uniform continuity. Okay, however, if the delta can somehow be chosen to depend only on the epsilon, so in other words, if we did, let's see, how do we, i.e., right, for other words, in other words, if for all epsilon there exists a delta that works for all C, so it reverses the order of those quantifiers. So now the choice of the delta is going to depend only really on the epsilon. Then we will say that f is uniformly continuous. And again, the abbreviation I'll use often is UC for uniformly continuous. So to be very technical, so that way we can see what the g-cap form is, we'll say that given a function f going from D to R, we say that f is uniformly continuous on D if for all epsilon greater than 0, there exists a delta greater than 0, such that when x and y are both taken from the domain D and our distance of x and y from each other is less than delta, these together will imply that the distance of f of x and f of y from each other can be made less than epsilon. So for the very observant student now, they might notice that this idea of being close to each other as opposed to being close to some point is very much like the Koshi sequences, and how Koshi sequences were different than general convergence of sequences. Okay, so for example, we know for lines in general that changes in the y as a ratio, or when written in ratio to changes in x, are held constant. In fact, that's what we generally called the slope, of course, right? So in that case, the delta would only depend on the epsilon, because all of the windows, if we were to draw a quick little sketch over here with a line, then no matter how big or where we put our epsilon, if we put our epsilon window up here, for example, or if we put an epsilon window over here, then as we came over to the function, we can see that if the width of the window was the same over here, I guess my window looks a little bit skinnier, so I'd have to go a little bit higher here. But if these two windows happen to have the same width along the y-axis, we can see that as we came over to the graph, that the windows down here would also be the same size. Right? Come over here, and at least approximately within the accuracy of the artist here. We can see that if our windows here were about the same size, then the windows down here would be the same size. So let's actually use the definition of uniform continuity and prove that the function f of x equals mx plus b, a standard linear function, is uniformly continuous. Okay, so our definition of uniform continuity was for all epsilon greater than 0. So we're definitely going to have to start off with let epsilon greater than 0 be given. Right, just like usual. And then second part of the GCAP is we had to choose a delta. So we're going to choose delta equal to, I'm not sure. Let's come back and see if we can figure out what it is. Okay, but after we choose that delta, we would then go with the GA part of the GCAP, which is we're going to assume that the distance between x and y's distance from each other for x and y in the domain is less than delta. And then we would have to go through our formal proof and hopefully prove that f of x minus f of y can be made less than epsilon. Right? Well, notice that f of x minus f of y, of course, would be what? Well, the function is mx plus b, so f of x would be mx plus b, and f of y would be my plus b. So if we subtract these from each other, we can see that the b's would cancel out, and we'd just be left with mx minus my. In other words, we'd be left with m times x minus y. Right, because the b's would cancel out with each other. Oh, and notice that this would be less than something times delta from right here, because we're assuming that x minus y, the distance of x and y from each other, is less than delta. Well, now that leads me to a possibility for what I wish for delta to be. Let's choose our delta in our argument to be 1 over absolute value of m. So in other words, 1 over the slope of the line. Ha ha ha! Because that's what's that going to cause down here now. This is going to be absolute value of m. Delta was 1 over absolute value of m. Yeah, whoops, not 1 over absolute value of m. We want epsilon over absolute value of m, because now this simply becomes an epsilon. Wow, right? So we have our proof. Okay, so let's try a little practice problem here. We're going to eventually be using the definition to show that certain functions are not uniformly continuous. So to that end, what happened here? Whoops, I don't want that on. So let's try to find the negation of the definition of uniform continuity. Okay, so recall, before we start to try to do this, let's recall the actual definition of uniform continuity. Right? What was the definition of uniform continuity? Well, what is this thing? We don't want to delete, we just want that to be shut down. Okay, recall that the definition of uniform continuity is f is uniformly continuous if for all epsilon greater than 0 there exists delta greater than 0 such that x, y are in D and x minus y less than delta together imply f of x minus f of y is less than epsilon. I'm sorry for this thing, I don't know what it is. Okay. So, what would the negation be? I encourage you to take a second here and pause and see if you remember enough from our logic class together to determine what the negation of this statement is, but assuming you took a second out here and tried it on your own, the negation of course would have to be that f is not uniformly continuous if for all is negated to there exists is negated to for all, The conditional's negation still needs to maintain the antecedent, so we still have x, y being in delta in the domain, and the distance between x and y being less than delta. But then we also had to have the consequent of that conditional be negated, and so here we would be requiring that f of x minus f of y happens to be bigger than or equal to epsilon. Okay, let's see if we can do this. Okay, so just to make sure that we see what it looks like in a picture here, a function like f of x equals x squared is not going to be uniformly continuous. This function increases faster and faster and faster for larger x values. So I drew a little sketch here of like a very rough f of x equals x squared. And notice that if I were to come along here and hit the axis, then I could take a fairly big delta around here and still fall within this epsilon redness of around the f of x1. But if we have approximately the same size, this is supposed to be about the same size as this, then if I come over to my function here, I can still find a delta, but notice that that delta is going to be forced to be really very much smaller, right? The delta really depends upon the point that's going into the function as the c. Okay, so here we're going to now prove formally that the f of x equals x squared is not uniformly continuous. Let epsilon equal 1, because we just have to show that there exists an epsilon that makes something happen. Now it has to be true for all delta, so we're going to let delta greater than 0 be given, because the negation required a universal quantifier over delta. Okay. Now let x equal 1 over delta and y equal 1 over delta plus delta over 2. You can refer to the textbook for the discussion that went into this, but we're just going to look at the proof and notice how this proves that this function is not uniformly continuous. The reason why this x and this y were chosen in particular was because now we could say that then, since these were chosen as x and y, you can see that the absolute value of x minus y, the distance between x and y, is, well, x is 1 over delta, and y is 1 over delta plus delta over 2, so when I subtract that off, it's going to be minus 1 over delta minus delta over 2. Get some nice cancellation, and the absolute value of a negative object is just going to be delta over 2, but this certainly forces x minus y to be less than delta. So we're making sure that we're taking points from the domain that caused this to happen, so we're ending up causing the distance between x and y to be less than delta, satisfying the antecedent. But now, what do we get? Notice that f of x minus f of y, we're hoping that we can show that this is bigger than or equal to some epsilon, and the epsilon that we chose was 1, so I'm hoping I can show this is bigger than or equal to 1. F of x minus f of y is equal to absolute x squared minus y squared, which is absolute x plus y, absolute x minus y, which is, because of the choice of x and y, 2 over delta plus delta over 2 multiplied by x minus y, but that's equal to delta over 2, and this is bigger than, inside of the absolute value here, I'm going to knock off this positive thing in order to make the inequality hold and be smaller. So go 2 over delta multiplied by the delta over 2, and what is that equal to? Well, that's equal to 1. In other words, that's epsilon. So we've shown that f of x minus f of y is in reality bigger than or equal to, in particular bigger than because of our choices here, it's bigger than epsilon. So therefore f is not uniformly continuous on R. Right? So what was the problem here? Well, the problem is that the issue was that we needed smaller and smaller delta for different points in the domain. or maybe bigger delta, right, would be possible if we had smaller points in the domain. And the point is that the delta was chosen in terms of the point in the domain because the windows were able to get smaller around the C's. So this can be actually avoided if we require the domain on which this is defined to be compact. We keep coming back to this compactness idea. The compactness is really, really beautiful in calculus. Remember, that's closed and bounded sets in R in the reals by the Heine-Borel theorem. So in fact, this leads us to a claim. The claim is that if we suppose f from D to R is continuous, and in addition to that we assume that it's on a compact set D, so the domain is compact, then f is uniformly continuous on that domain D. Okay, and just to introduce you, we're going to go over and do the problem. We're going to prove this in a moment on the next couple slides. It'll take me a couple slides, but always keep in track in your mind or on a piece of paper. You might wish to write this down so we can refer to it later. When we show uniform continuity, we're going to need to show something about an f of x minus an f of y being less than some kind of epsilon, right? That's going to be kind of a big goal. So in order to do this, I'm going to have to make the distance between an f of x and a f of y become controllable. And I am going to do that by finding a very, very special point, an f of x sub I, in which I can essentially control this bit and furthermore control this bit. And if I can control both of those, for example, make them both less than epsilon over 2's, then that's the thing that I'm going to be able to make less than epsilon and control the definition of uniform continuity. So take a snapshot or some kind of screenshot of that little picture there, and that's going to be our big goal as we progress through a 2-page proof. This one's going to take 2 of our little slides here. Okay, of course we're going to be proving uniform continuity, so we've got to put our G-caps on. First line, let epsilon greater than 0 be given. Very predictable, right? Now, since f was continuous on the set D, then given any x in D, there is a delta sub x greater than 0 with f of x minus f of y being able to be controlled to be less than any positive number. So we'll make these be less than epsilon over 2. Wink, wink, right? Remember, we needed that to happen eventually. When we have x minus y, the distance between x and y, being less than delta, and y just simply being a point from the domain. So if you look back at the definition of continuity, you might be thinking, oh wait, there's a C floating around, right? There's a C and D and all of these things. Well, in this problem, you can sort of think of the, let's see, what would it be, the x or the y? This is for all x and d, x minus c, c and d. So in this effect right here, we're kind of like the y is acting like the c from our old definition. Alright, so look back at that definition, and here I'm using x's and y's because that's the notation of uniform continuity, but the idea is no different than before. We're just letting this y kind of act like the c from that definition. Okay, so as long as you accept that, it is the same definition, I promise here. We can now notice that f, if we let f be the set of neighborhoods of every x value in the domain, with a radius of that delta x that we know exists by continuity over 2 for all x in the domain, this would be an open cover of D. Can you guess where I'm going now? D was compact, remember. Right? So since D is compact, then this open cover must admit a finite subcover. So since D is compact, let D be a subset of the finite, some finite subcover of, let's say, a neighborhood x1, delta x1 over 2, union up to some finite point. That's the point of compactness, is that we don't have infinitely many of these. And we'll let this one be x sub n delta xn over 2. And that's finally going to give us the opportunity to choose our delta. So remember, we had let epsilon be given. We did all of this discussion so that we can now finally choose our delta to be the minimum of all of these little delta x1s over, or delta xi's over 2. Delta x1 over 2, delta xn over 2. Right? So let's think about this for a second now. Assume, right, next part of the GCAP, assume x and y happen to be in the domain and the distance between them is less than this delta, which is less than each one of these delta xi's over 2, which causes the distance between any 2 points to be less than epsilon over 2. Can you show the last part that we need? Can you show f of x minus f of y is less than epsilon? Pause the video for a moment and see if you can do this on your own. Hint, it's going to take a couple of triangle inequalities, but I believe that many of you can actually try to do this and complete it on your own. Assuming you took a moment out here, let's do our proof continued and actually finish it off. Okay? So now, what do we know? We know x is in D, right? It was in the domain. So x is in some neighborhood of some xi, delta xi over 2 for some I. Remember, these were the finite subcover, so it wasn't all of them, but even though we don't have the delta x from the one that was the continuity for x, we know we have a finite subcover, so x itself must lie in one of those neighborhoods. We're not sure which one, but it has to lie in one of them. So what do we get? We have that x minus y is less than delta because it was equal to the minimum. This was the minimum of all the delta xi over 2's. So it's definitely less than the ones we need. So we forced x minus y to be less than or equal to delta xi over 2. Thus, so therefore, y minus xi is equal to y minus x plus x minus xi, which is less than or equal to y minus x plus x minus xi. There's our triangle inequality. This is less than delta xi over 2 because that's from the minimum delta, right here. And this one's less than delta xi over 2, and that's from the fact that it's in this one in particular, right? Or x minus xi, sorry, is in this window of xi minus 2. So we're less than delta xi, right? So now by the choices of the delta xi, by the choice of delta xi, these came from the continuity of the f's. What do we get from here? We get f of y minus f of xi is less than epsilon over 2, and f of x minus f of xi is also less than epsilon over 2. Right? The distances between the x's and the y's. So finally, we get the big conclusion that we wanted. F of x minus f of y. Get ready for another triangle inequality here. F of x minus f of xi plus f of xi minus f of y. This is the triangle inequality that was pictured in that initial red line that we drew at the beginning of the claim. This is, not equal to, this one would actually be less than, triangle inequality, I guess less than or equal to here, f of x minus f of xi plus f of xi minus f of y. But as noted right here and here, this is less than epsilon over 2 plus epsilon over 2, which is epsilon. Yay! So the compact sets do what we want. Amazing! So although f of x equals x squared was not uniformly continuous on all of R, right, it wasn't uniformly continuous overall, the previous theorem is implying that f of x would be uniformly continuous over, say, a compact set. So f of x equals x squared would be uniformly continuous on a set like, let's say, AB. This is a closed bounded set in R, so we're getting uniform continuity over that set. How can we see that? Let's put our g-caps on. Let epsilon greater than 0 be given. Choose delta to be equal to, oh, I don't know. Let's think about it for a moment and see if we can find something. If we assume that x minus y is less than delta, then notice f of x minus f of y is equal to absolute value of x squared minus y squared, and that's equal to x minus y, x plus y, and that's less than, well, because of this x minus y is less than delta, this would be less than delta x plus y. Now, what is the absolute biggest that x plus y could ever be? Well, we're on a bounded set now, right? So no matter how big, how far away can x and y actually be from each other? How big can these actually be? Well, the biggest value for these would be something like the end points, right? How far apart could these points be? They would have to be, oh, I think I made an error when I did this. I think we would have to let D be, I would have to let this one be epsilon over 2 times the max of absolute A and absolute B. Right, for example, I don't know where these ones are coming from. I don't know what the numbers themselves are, but x plus y could theoretically be which one of A and B's absolute value is the largest, and maybe we take that number and a number that's really, 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 really close to it. So like on the interval from the textbook, I think they did -5 to 5, so let one of them be 5 and let the other one be 4.99999, and you can get all the way up to 10. Okay, so that means that this right here is going to cause, if we choose this, then no matter what value, the biggest we can possibly make x or y be is whatever the end point's maximum absolute value is. So this is going to control this to be less than, so essentially become equal to epsilon over 2 times the max of it. Maybe I should say it like this to make it more like our other ones. This would be delta multiplied by epsilon over 2 times the max. Oops, sorry. This would be, what's the biggest this could be? Would be 2 times the max of whatever absolute A and absolute B are. But then this would be less than, the delta was chosen to be epsilon over this 2 max multiplied by the 2 max, canceling out to give us the epsilon. Great save, Josh. Because I had b minus a, but of course b minus a would be the distance of the entire interval, but the values inside of the interval might be larger. I mean, who knows? So I saved it there, I think. Okay. Here's a practice problem for you then. Can you find a continuous function f in the going from D to R and a Cauchy sequence, to relate this back to Cauchiness now, such that f of xn actually becomes divergent? So we have a convergent sequence xn, a Cauchy sequence I should say, and a divergent image. So pause for a moment, see if you can do this. As a fairly simple example, let's let f of x equal 1 over radical x on a domain that is non-compact, like 0 to 1. Let xn be defined as 1 over n squared. So this is definitely a Cauchy sequence, right? Things are getting very, very, very close to 0 in the compact set 0 to 1, so this is Cauchy because it converges. But what happens in this set? Notice it's Cauchy but non-convergent because 0 is not part of this domain. But what is f of xn? Well, f of xn is 1 over the radical of 1 over n squared, which is 1 over n, which is n. And n diverges to positive infinity. So that actually leads us into the relationship between uniform continuity and the Cauchy sequences. I claim that if f is a continuous function, if f is a function going from d to r and it's uniformly continuous on d, and, not and, but and, xn happens to be Cauchy, then f of xn is also going to be Cauchy. And the proof here is actually not terrible. If you dig through the definitions of Cauchy and uniform continuity, they already have some similarities, the x's and the y's, the close to each other instead of being close to a particular limit. So you might even be able to jump onto this on your own. But let's do it together. Maybe pause the video again, see if you take a second here and try to do it on your own. But if we let epsilon greater than 0 be given, what was the definition of uniform continuity? Since f is uniformly continuous, we can let delta, we get to have a delta, we don't have to choose it, we know that there is a delta that exists, and we let delta be such that x, y in d force, if x and y are in d and the distance between x and y happens to be less than delta, we will let those together imply that we have f of x minus f of y being less than epsilon. Okay. Furthermore, we also know that xn is Cauchy. So with xn being Cauchy, what do we get from there? We can find a capital N such that xn minus xm being less than delta, or xn minus xm can be made less than any positive number, in particular delta, for n and m being bigger than or equal to capital N. Right? The Cauchy sequence was there exists an n such that we can make the distance between our terms become as small as we want. So we're going to force them to be less than delta. Because if they're less than delta, that's going to imply f of x minus f of y is less than epsilon. Right? So finally, for mn bigger than capital N, we see f of xn minus f of xm is made less than epsilon, right? Because we made sure that we were less than delta, and being less than delta apart implied that we were less than epsilon. So overall, what do we get? We get that f of xn is Cauchy, because there existed an n for which the distance between terms of the f sequence ended up becoming less than or equal to epsilon. MWO. Whoa! Okay, now what that previous theorem provides for us is a pretty test to see if a function is continuous on an open interval. Remember, an open interval is non-compact. It's bounded, but it's not closed. So essentially, informally, this test will say that essentially it is continuous if the pretty test to see if f is continuous on, actually even if we know it's continuous. So we want to say here uniformly continuous. M is uniformly continuous on an open interval is essentially it is uniformly continuous So let's erase this. It is uniformly continuous if it can be extended to a function that is simply continuous, not uniformly continuous, on the closed interval a to b. Because we would know that if we could extend it to a continuous function on closed interval a to b, then it would be uniformly continuous on a to b, and therefore it must be uniformly continuous on the open subset where we take out those two endpoints. And it requires this Cauchiness because you can actually like slide in on the sides. You can use the limit of the left and the right endpoint using the Cauchiness. Things get really close to some value even if it's not in the set, to be able to extend the definition of the function to hit those points. So very formally now, the formal claim would be that a function f going on the open interval a to b to r is uniformly continuous on that open interval a to b if, and actually only if, it can be extended to a function that is continuous on the closed interval a to b. The proof of this is in the book. It's not terrible. You just take the limiting values on the outside of the set from the Cauchiness, but we will actually just look at this more as an application. How can we use this to apply it to problems? So think about it, practice. Let's take a second, pause if you wish, and let's see if we can show that f of x equals x sine 1 over x is uniformly continuous on the open interval 0 to 1. Okay, after you pause, assume you've paused and tried this for a second, well, notice that f of 1 is just equal to sine of 1. And that's a number. That's a real number. No big deal there. And f of 0 does not exist. But the limit as x approaches 0 of f of x does exist. We showed this in the last units, that this is equal to 1. So here's our extension function. We let g of x equal the function 1 if x happens to be equal to 0, and we let it be x sine 1 over x if 0 is less than x is less than or equal to 1, even though that's not f because it's only on the open interval from 0 to 1. But we threw in the limit at 0, which is where this is not existent, and then we just let it go all the way up to 1 because 1 can be filled in just by filling in the value. So this is continuous on the closed interval 0 to 1, so f is uniformly continuous on the open interval 0 to 1. So we just extended it to a continuous function on the closed interval. Pause for a second on this one because we've done this one similarly in another unit and shown something about this particular function at 0, and see if you can show that this function is uniformly continuous. Okay, pausing for a second and assuming that you've tried this and come back and you're hopefully pleasantly surprised or maybe frustratingly surprised that recall the limit as x approaches 0 of sine of 1 over x does not exist. So it's not that the functional value doesn't exist, but this one's limit didn't even exist. This was a rapidly oscillating function. It would go up and up and down and up and down and up and down really, really, really fast as you got close to 0. So it cannot be extended. We have no limiting value, so it cannot be extended to a continuous function on the closed interval a to b, or on the closed interval 0 to 1. In particular, at 0 was the problem. We can't extend it at 0 because there is no limit. So since we can't extend it, we can't fill it in, and it was an if and only if statement in that claim. That means this f is not uniformly continuous on the open interval 0 to 1. Okay, your homework, should you choose to accept the challenge, is problems 1, 2, 3, 9, 10, and 14. Good luck.